Hello, this is Professor Matt Katroulis, and this is the first in a series of videos that I'm going to be putting up for my students in Chemistry 230. The purpose of these videos really is to address some of the topics that you already should have seen in general chemistry, if not preparatory chemistry, just to give you a quick review of those, so that way we can spend more time in our lectures focusing on topics which are new and perhaps more difficult than these which you already should have seen. So this first video lecture is going to address the material in sections 1.6 and 1.7 from the textbook, which is material about atomic orbitals and materials on valence bond theories. And from there, we're going to spend even more time talking about bonding theories and other related subjects such as hybridization. So let's go ahead and get started here. Okay, so we're going to start off with talking about atomic orbitals. Just to give you a real quick review, if you remember that whole stuff about S, P, D, and F, those were your atomic orbitals that you learned about in previous classes, and that's really what we're going to be focusing on right now. So if we go ahead and we think back into the development of atomic theory, we know that quantum mechanics was used to describe a lot of the interesting behavior that was observed for very, very small particles, for example, electrons, atoms, molecules, etc. And we know, for example, that just like light has properties similar to waves and similar to particles, for example, the wave-particle duality, we see that the same is true for matter. And in particular, we're going to be looking at this for electrons. So ultimately, we have wave equations which describe the wave-like properties of electrons. And as we see here on the screen, the solution to those wave equations give you these visual pictures that we're going to call orbitals. Now, as far as our orbitals go, each of these wave equations can be solved to give us a different type of a shape. In some cases, the shape is very simple and easily described, like, for example, the shape below that we're seeing for an s orbital, which is a very simple sphere. And then other times, they can get extremely complicated looking. For example, some of the f orbitals and even the d orbitals can be rather complex and not easily described in words. Now, the types of orbitals that we see here are going to describe essentially a probability of finding an electron in a given region. And as we see here, this particular picture of an orbital, a 1s orbital, is essentially describing the region where you have 90% likelihood of finding an electron, which is said to be within that orbital. Now, we're saying 90% here. You can actually solve the wave equations and show them, represent them with a 99% probability or a 95% probability if you wanted to do so. In this particular case, we're just going to use orbitals that have been drawn to show a 90% likelihood. Okay, and the idea here is as you move further and further away from the nucleus, which would be at the origin of this figure, you would be less and less likely to find the electron. In theory, it never actually dips down to 0% at any particular location. It just, the likelihood of finding an electron very far away from that nucleus just diminishes rather rapidly. Okay. So, as I had said earlier, electrons behave both like particles and like waves. And we have seen experimental data which will verify this. And in some cases, we will refer to that later on as we go in the semester. So if we go ahead and we take a look here, what we're using here is the Greek letter psi, and we are representing it as our wave function. Okay, a wave function can be positive, and we're color coding that as red in this particular case. And a wave function can also have a negative value, and it can be 0. Now, it's very important that you not confuse the value of the wave function with charge. For example, we don't say that the electron is now positively charged when the wave function is positive and negatively charged when it's negative. No, an electron is always negatively charged, okay? It's more like just a simple matter of thinking about amplitudes, so to speak. So it's best to think of this as, for example, a positive amplitude and a negative amplitude, just like if we're looking at sines and cosines. This is very similar the way this is drawn to a sine curve. And of course, it can pass through a point which is going to be zero valued. Now off to the right, we see an orbital that should be familiar called a p orbital. And we see the same type of color coding that we saw on the last slide. Red indicating that we have a positive sign associated with the wave function, and blue indicating that we have a negative sign. And again, not charge, not good and bad, it's just the sign right there. So as I'd mentioned before, sign has nothing to do with charge in this particular context. Now, the difference between this orbital that we see here, and if we go back and look at the last one, our s orbital, you see our s orbital here has been drawn as blue, which might imply that it has a negative wave function all the way throughout, although the sign is entirely arbitrary. What we are showing here is there's some definite differences. There is a difference of sign here. And although we're saying red is positive and blue is negative, we could have just as well looked at it exactly the opposite and said, well, if blue is positive, then red is negative. Again, it's an arbitrary decision. But you'll notice that there is both amplitudes shown. And very importantly here, we have what is called a nodal plane. I haven't drawn the plane in right here, but if you imagine, for example, that this is along, let's call this for the time being, let's just call this the z-axis, okay? Then right here, the xy plane would be a nodal plane. And on the one hand, we might want to define that as, an area of zero probability of finding the electron. Or what we might want to just do, and I think this is a more accurate description, even though it's a little bit more abstract, is to just say that that is a region where effectively the wave function goes to zero. Okay, so these nodes are going to be seen in a lot of both atomic orbitals, and then we are going to see them as well when we get to molecular orbitals, well, there will be of particular significance. Now, when we go ahead and look at all the different orbitals that electrons can fill, and specifically within the context of subshells, which are collections of those orbitals, we find that the lowest energy subshell, the one with the lowest energy orbital, is the 1s orbital. And in general, if you go ahead and start plunking electrons into atomic orbitals, if you could do it that way, you would find that the first two electrons that you supply should always go into the 1s orbital. And that 1s orbital, as you'll recall, makes up the 1s subshell. And since an orbital can only hold 2 electrons at most, and there's only one orbital in a 1s subshell, we are full once we get to 2 electrons there. Okay? It simply cannot fit more within that. That is the maximum region which is assigned to a 1s, to any orbital, 2 electrons. And then the 2s orbital would be the next orbital that we fill, and that is in the 2s subshell. Now, unlike the 1s orbital, the 2s orbital does indeed have a node. And we can see that here because we have a difference in colors in the wave sign. And in fact, that nodal plane is right there on the surface of that sphere. And again, the easy way to think about that might be to say, well, that's a region where the electron can, not be found. A more accurate picture would be to say, well, that's where the wave function essentially goes to zero. It's almost like you could think the electron seems to just blink out of existence at that point. It's not, again, an entirely accurate description, but when we're trying to think of quantum mechanics, we want to come up with models that describe it, and that's a kind of an easy way to go ahead and describe it. So it's right along that sphere. And how many electrons could we fill in here? Again, you could fill in at most 2 electrons. Okay. Now, once you've filled up the 2s orbital, which is the only thing that makes up the 2s subshell, then we go on to the 2p subshell. And the 2p subshell consists of 3 orbitals. And if we're going to go ahead here and give them specific names, we have the py orbital, okay, on the second subshell, so 2py. which is along the y-axis, and then we have one along the x-axis and one along the z-axis. Again, if we were to try to identify these, they are, completely arbitrary. If I rotated this and called this instead the y-axis, then this would have been the 2py orbital. Okay. Now, these are degenerate, and degenerate means essentially that electrons within them have the same energy. Okay, and we're going to use that term quite a bit. Where are the nodes as far as each of these goes? Well, if you're looking at 2py, the nodal plane is the xz plane. In the case of the 2px orbital, the nodal plane is, just look at the variables that are not used here, y and z. It's on the yz plane. And then for the 2pz orbital, it's going to be the xy plane where the node occurs. And just for ease, we have not ease of viewing, we have not shown the actual nodes here as planes because that would kind of abstract part of the picture, make it unclear. All right, you should already know how to come up with the electron configurations for several elements here. So if we just look, for example, at the first 8 elements here, we see that the first electron goes ahead and, as we said earlier, does not fill, but is added to the 1s orbital, which is the only thing in the 1s subshell. Helium, we get 2 electrons, and now we notice that this orbital is full. Remember that the lines represent orbitals. Okay. Moving on to lithium, we see that the 1s orbital is full, therefore the 1s subshell is full. Then we go on to 2s and we put in 1 electron. With beryllium, we add another one. We have 4 electrons. Okay. Now with boron, we are going to start using the 2p subshell. Okay, the 2p subshell. We have 3 lines there to indicate our 3 orbitals. They are at the same energy level, so that means that those orbitals are degenerate. And you'll notice the process here of adding electrons one at a time into each of those orbitals. And then once each of those orbitals has 1 electron, we are going to go ahead and then start doubling them up. And you notice by convention, we double these up from left to right. Now, you should recall that we have 3 important rules that govern how we go ahead and supply these electrons. The first rule that we're demonstrating here is the Aufbau principle. And you will recall that the Aufbau principle says that when we're dealing with atoms in their ground states, we should always fill electrons in order from lowest energy to highest energy. So for example, the Aufbau principle here tells us that we should be adding the electrons to the 1s subshell before we go up to the next highest subshell, which is 2s. And then once that's full, we start adding electrons to 2p. So the Aufbau principle is our first rule. So the next rule that we're going to examine here is the Pauli exclusion principle. Now, if we look at the Pauli exclusion principle in its most complete form, what it tells us is that any 2 electrons that we have in an atom must have different quantum numbers. To simplify that a bit, a consequence of it is that any 2 electrons in the same orbital must have opposite spin. And we see that, for example, from helium on in the 1s subshell. These 2 electrons have opposite spins, spin up and spin down, which we're representing here with the sign of the arrow. Okay, so that is a consequence of the Pauli exclusion principle. And then finally, another rule that we must look at is Hund's rule. And Hund's rule starts to take effect when we see a practical example here for comparing boron and carbon. When you came in to fill in the electrons for carbon, you had a choice. Did we want to put this second electron in the 2p subshell with the electron that was already in this orbital, or should it have been filled into one of the vacant orbitals? And in fact, we see that when we are filling up the orbitals, we always want to give each orbital 1 electron at a time until each of these orbitals in a subshell are full. Again, this applies to orbitals that are in the same subshell, degenerate orbitals. You'll notice here that with nitrogen, all of the orbitals are singularly filled. There is one electron in each of these. So when we get to oxygen, we now have to start pairing up electrons. And you'll notice, again, as a consequence of the Pauli principle, this fourth electron that we've added to the subshell must have an opposite spin to the electron that was already there. So again, we have our three rules. They are Aufbau, which basically tells us that we fill from lowest energy to highest. The Pauli exclusion principle, which says that electrons that are in the same orbital must have opposite spin. And then Hund's rule, which says that we fill each orbital in a subshell with one electron before we start pairing them up in their most simple forms. Okay. Now we're going to get to look at how do we start generalizing bonds. How do we look at bonds in terms of putting them together? And the simplest way to do this is to say, well, let's go ahead and take the atomic orbitals and just start putting the atomic orbitals together to give us bonding orbitals. It's kind of a simple way to do it. Does it work completely? As we're going to see, no, but it's a good starting point for looking at these. So we've already talked about electrons and their wave-like properties. So let's say that we are going to go ahead and start pairing electrons together in a bond. So this dot will represent our nucleus. We go ahead and start bringing the nucleus closer and closer together. And what we see here then is the electrons' wave properties will have an overlap. In this particular case, the sign of the wave functions is the same. We've color-coded that red here. And what we will see is that there is what we call a constructive interference. Those waves actually add to one another to generate a larger amplitude wave. And in fact, this would essentially represent what we would say is our molecular orbital here, because it's coming together from a bonding perspective here. Or we could go ahead and instead add waves that have opposite signs. And if we do that, what we ultimately see here is a canceling. If we were to add this picture over to this picture, as it were, and at one point we would see that the amplitudes would actually add in a way, such a way as to cancel each other out. In other words, at this particular point, this wave is just as positive as this one is negative, and so we have destructive interference. And where that occurs, we get a node. And again, that node is where the wave has zero amplitude. Now, when we talk about whether we get a bond or not, we have to look at whether the interference is constructive or destructive, and only constructive interference results in a bond. That doesn't mean we can completely ignore destructive interference, though, because that's going to lead to what we are going to call antibonding. Okay, so if we're going to use our very simple valence bond theory model here of how we might form an H2 molecule, we know that each one of these atoms, which we're representing here, and we're looking specifically at their 1s orbitals, there's one electron in each of these. If we go ahead and we bring these guys as close as we can, that the nuclei will allow before the repulsion gets too great between them, what we see is we have a region of overlap, and that's going to be a constructive overlap if these are of the same wave function. We've got them color-coded blue, so we will assume that the wave function is going to have the same sign. And so what we see is a constructive overlap. We've created a bonding orbital between these two hydrogen atoms to give us a hydrogen molecule. Where are we going to find the bonded electrons most of the time? Well, it's just like we look at atomic orbitals. You can look and see here, where's the largest volume? The largest volume here is represented by this space here in between those two atoms. So we would expect the two electrons to spend the majority of their time in between that space. In fact, the electrons can, in fact, move over this whole space, and they are not constrained to this space. You know, the electrons, one of them or both of them at any point in time, could move out of the space. It's just that it's not very likely. Again, these pictures represent probabilities of where you're going to find the electrons.